Hello and welcome to everybody. This is Pablo Rivier. I am staff astronomer in Observatorio Astronómico Nacional in Madrid, Spain. And I'm going to give you a short presentation about ABR-IGA, which is called ABR-IGA, a Rosetta Stone for Planet Formation Theories. So why ABR-IGA? ABR-IGA is a well-known protoplanetary system in Taurus, which, as we know, is a pristine location for studies of protoplanetary disk and planet formation theories. ABR-IGA is a prototypical Herbig star surrounded by a transition disk with a large inner cavity that extends out to 100 AUs, more or less. The disk has been observed at multiple wavelengths and shows a plethora of features that can be explained by the presence of a planetary companion. Such features include a dust cavity, a spiral arm, and an azimuthal asymmetry in the form of a dust trap. Spiral arms have been detected, for instance, at many different wavelengths. They have been detected in near-infrared scattered light images, as you can see here, but they have been also observed in CO, for instance, by Tang in 2017. We also know that there is a large dust cavity extending out to 100 AU, more or less. This has been observed first by Pietu and Tang, and it was also observed by Fuente in 2017, as we can see here. So the fact that there are a cavity and spiral arms might be explained by the presence of a planetary companion. And the presence of a dust trap can be explained by the presence of a planetary companion too. So aiming to see whether this explanation was true for the case of ABR-IGA, Fuente et al. In 2017 performed a series of other hydrodynamical simulations consisting of a central source surrounded by a protoplanetary disk, a dust cavity covered by a Jupiter mass planet located at 96 astronomical units. You can see the results of the simulations in the bottom panel of this figure. In the top panels, we have the observations by the team. And as you can see, the model reproduces quite well the observations, exception made of the compact source towards the center. And so apparently, the presence of a 2 Jupiter's mass planet at 96 AU can explain our millimeter observations. In this panel, I am showing you our observations of ABR-IGA performed with the NOEMA that were published in our paper in 2019. We observed HCO plus 322 and HCN 322, and we observed a series of very interesting features, including the gas ring that is more or less coincident with the dust ring, strong azimuthal asymmetries, and also a crescent shape that is more or less coincident with the dust trap in the continuum. And more precisely, in the HCO plus, we observed three interesting features. First, we observe that HCO gas is filling the dust cavity. Second, we see a strong emission towards the center that is not observed in HCN. And third, we see a very interesting filamentary structure that is connecting the outer ring with the inner compact source. In this panel, I show the Tang CO observations, as well as our observation of HCO plus. And as you can see, the spirals detected by Tang are more or less coincident or co-spatial with our filamentary structure. What we also saw was that there was a strong anomaly associated with the filamentary structure in the velocity field, and also that in the velocity field we saw twisted isophotes that can be a signature of an outflow or an inflow, or to the presence of two misaligned disks. Aiming to see how can we explain the anomaly observed in the velocity field, we developed a toy model consisting of two protoplanetary disks, an inner one extending out till 45 AU, and an outer one extending out till 350 astronomical units, with the inclination and position angles that you can see here. And those disks were surrounding a 2.4 solar masses star. With this, we created the velocity map, and we subtracted the velocity map from our moment one map. And you can see the result of this subtraction in this figure. And the interesting thing is that the more prominent residuals are observed toward the residual position. So to try to better understand what was going on, we did this cut along the filament, and we studied the velocity along this cut. And what we saw is that to the northeast, where there is no filamentary structure, the velocity cut is well reproduced by the two Keplerian disk model. But when we go to the southwestern side, we see that there are strong departures and that we need free-falling material to explain our observations. This apparently means that we have a radial inflow of material that is connecting the outer disk with an inner disk. And this is a very interesting feature that needs, of course, further research. In this slide, I am showing you the observations by our team. These observations were recently published. We observed 12CO, 13CO, C18O, formaldehyde, and sulfur monoxide. And there are very interesting features that can already be observed in the maps. First, in the 12CO maps, and also in the 13CO map, we see hints of large structure spiral arms. In the C18O map, we see something that is quite similar to the continuum map. In formaldehyde, we see something very similar to C18O, but with a strong azimuthal asymmetries. And in the sulfur monoxide map, we also see these very strong azimuthal asymmetries, and also a filamentary structure that seems to be coincident with the one observed in HCO+. Since we observed the optically thick 12CO line, we were able to retrieve a temperature map that shows us that the temperature goes from 10 in the outermost regions of the system that are dominated by envelope emission to 70 in the innermost region. These temperatures are very similar to the ones that we can derive using formaldehyde, that range from 29 to 71 with a mean temperature of 39. And since we observed that also 13CO, we decided to perform, to create a gas to dust ratio map, which is what we show here. And it's a very interesting map that tells us two interesting things. First, along the ring, we have gas to dust ratios that go from 30 to 70, so well below the canonical 100 value. And also in the dust trap, we reach values as low as 8 to 16. So this is in perfect agreement with previous observations and theories that point to very low gas to dust ratios along dust traps. In this figure, I am showing you the radial profile of the intensity of the different lines, including also HCO plus and HCN. And what we can see is that there is a strong chemical segregation. ACO is the species that is located in the outermost regions, 12CO and HCO plus in the innermost regions, and in between C18O and formaldehyde and HCN. So apparently we have a very strong chemical segregation in this system. One question that comes to mind when one sees these radial profiles is whether the layered structure is related to the different snow lines. If such was the case, one would expect that the location of the radial peak will be correlated with the will be anticorrelated with the binding energy, but this is not what we see. We almost see the opposite. So apparently, this is suggesting us that thermal desorption is not driving the chemical composition and the spatial distribution in this very interesting disk. Aiming to better understand what was going on, we developed a series of astrochemical models using Nautilus. We ran the series of models that you can see here in the legend. So we tried two gas to dust ratios, 40 and 100. We tried two sulfur abundances, 1.5, 10 to the minus 5, and 8, 10 to the minus 8. And we also tried oxygen poor and oxygen and normal oxygen abundances. You can see here a comparison of the profiles of the different models and the observed column density radial profiles. And the conclusion from this very interesting comparison is that the best fit model is one with a low gas to dust ratio around 40, which is in agreement with what we saw in our gas to dust ratio map, that we need sulfur depletion, and also that we need oxygen depletion. So this is in agreement with previous studies that point to the fact that evolved disks are oxygen depleted, but we also see hints of sulfur depletion. And finally, and to summarize, well, ABR-IGA is a very interesting source with with a dust cavity, spiral arms, and azimuthal asymmetries. So features that can be explained by the presence of a planetary companion. There is a very interesting filament connecting the outer disk and the inner compact source that is present in HCO plus maps. And it seems to be tracing an accretion flow. However, further research is needed. We see hints of a strong chemical segregation. We see that both models and observations seems to be better fit with a gas to dust ratio of 40. And also models are telling us that we have a strong sulfur depletion and also oxygen depletion, which are signatures of an evolved disk. And this is all I wanted to show you. Thank you everybody for watching this presentation.